Hey everyone, Sharan here. I'm an AI engineer at Prediction Guard. What you're about to watch is a project walkthrough from a team of students at the Purdue Data Mine who spent this past year working with us on something I think is genuinely important, that is red teaming agentic AI systems against the OWASP agentic AI top 10. Quick context of why this matters. Agentic systems are getting deployed in production faster than the security frameworks around them are maturing. Most enterprises are still figuring out what the attack surface even looks like when you have an agent that can plan, use tools, and act on its own. What makes this team's work especially valuable is how they structured the evaluation. They ran attack against agentic systems in two configurations, one without any safeguards in place and one with prediction guards, governance policies, and safeguards layered into it. That setup let them do something most red teaming exercises don't, that is, actually measure the efficacy of the controls and not just the catalog vulnerabilities. The before and after comparison gives a real signal on where prediction guards safeguards hold up, where they need to evolve, and what enterprises should be thinking about when they put agents into production. I got a chance to mentor this team throughout this last 2 semesters, but the work you are about to see here is completely theirs. They built it, they broke things in interesting ways, and they are going to walk you through what they have found. Big thanks to the team and Prediction Guard and to the Data Mine program for this partnership. Over to them now.
So, hello everyone. To kick things off, I wanted to start by addressing why we are suddenly so concerned about agentic AI. And when we've been using chatbots for years, and we haven't really been concerned about this at all. So, here's the thing: a traditional large language model is essentially passive. You can think of it like a highly intelligent librarian. You can ask it a question, it searches its knowledge, and then gives you an answer. That's it. It doesn't really take action. It doesn't make decisions beyond generating text, and it stays within a very controlled boundary. But agentic AI completely changes that. Now imagine giving the same librarian not just books, but keys to the building, access to internal systems, and even a credit card. So it's like taking actions on your behalf. These agents can execute multi step workflows, interact with APIs and tools, access private databases, communicate with other agents, and make decisions without constant human oversight. So, that level of autonomy is what makes agentic AI incredibly powerful, but it's exactly what makes it dangerous as well. Because once an AI system can act and not just respond, the consequences of failure become very real. It's no longer about generating a wrong sentence, it's about deleting a file, leaking sensitive data, or executing an action that you don't want to happen. And that leads us to the core problem, a massive expansion of the attack surface. If we deploy what we call a naked LLM, meaning a model without proper safeguards, we are essentially leaving every one of these capabilities exposed. There are no guardrails controlling what the agent should or should not do. That's exactly what our project set to investigate.
In collaboration with Prediction Guard and the data mine, our goal was not just to build agents, but to break them. We approached this from a red teaming perspective. Instead of asking, how can we make this work, we asked, how can this fail, and how bad can it get? And more importantly, can safeguards actually prevent those failures in a measurable, reliable way? To make this rigorous and not just anecdotal, we grounded our entire project in the OWASP top 10 for agentic applications. These are not theoretical risks. They are well-defined, structured categories of vulnerabilities that specifically target how agent-based systems operate. Let's walk through them because understanding these risks is key to understanding everything that follows.
Okay, next slide, please. All right, so I'm going to lead us into talking about risk 1 and 2. So the first risk is agent goal hijacking, and this is when an attacker manipulates the agent's objective. So like a simple task like summarize this email can be turned into like forward this email to a competitor. So the agent isn't actually aware it's being tricked, it just follows the instruction that you give it, right? And the second one is tool misuse. So agents have access to tools like APIs or databases. And if misused, those tools can expose private data or perform unauthorized actions.
Going into risk 3, which is identity and privilege management, agents often inherit sensitive permissions. So if those permissions are too broad, then the agent can access sensitive information that it should never touch. Risk 4 is supply chain vulnerabilities. If an external plugin or dependency is compromised, the agent itself becomes compromised. So it's like installing malware through a trusted extension. Risk 5 is remote code execution. This is one of the most dangerous ones. An attacker can trick the agent into running arbitrary code on the system, and that would expose a lot of bad things. Oh, sorry. And then risk 6 is memory and context poisoning. Agents rely on memory and retrieval systems such that if the memory is corrupted, the agent's behavior can be manipulated over time. Shivin will talk about risk 7.
Yeah. So going into the last few risks, risk 7 is inter-agent communication attacks. So this essentially means that in multi-agent systems, the agents will talk to each other, and if those messages are intercepted or spoofed, it can create a system-wide confusion or even data leaks. Risk 8 is cascading failures. This happens when there's a small error in one step, which can propagate across an entire workflow, creating large-scale system failures. Risk 9 is trust exploitation. Humans tend to trust AI outputs, and so attackers can exploit this by making the AI produce convincing, harmful instructions. Risk 10 is rogue agents, and this is the worst case scenario. The agent becomes fully misaligned and starts acting independently in harmful ways.
Sorry, my audio is lagging a lot. But I will talk about the methodology. Now, instead of just studying these risks theoretically, we built a system to test them experimentally. We designed 10 adversarial agents, each intentionally vulnerable to one specific OWASP risk. To ensure consistency, we enforced something called an agent contract. Now, every agent had to implement the exact same interface, a single run function, with standardized inputs and outputs. What this means is that that every agent became interchangeable. We could plug any agent into any test and evaluate it under identical conditions. On top of that, we built a shared runner, which acted as our experimental engine. This system allowed us to automatically run every agent against every relevant test case under multiple configurations and log the results in a structured format. This allowed us to move from isolated demos to real comparable data.
You're muted, Tony, if you want to start over.
Okay, so to make the results scientifically valid, we followed a 4-configuration testing protocol. First, we run a baseline model with no safeguards and compare it with the same model with safeguards enabled. Then we run secondary model with no safeguards, and then the secondary model with safeguards enabled. This wasn't about measuring performance. It was about answering 2 key questions. 1, do the safeguards actually work? And 2, do they work consistently across different models? So here I will run a demo to show how it works. So this is a CI demo for our project. And from here, you can see the ASI, different ASI risks that we are trying to hijack. And for example, if I choose 3, which is identity and privilege abuse, you can see that we're using the GPTOS S120 billion model, and currently the safeguard is not on. So I can choose an attack prompt or type my own prompt, and in this situation, I'll just choose one of the prompts. Let's say I'll just try to ask the AI to delete the user. So I use this prompt and I let it run comparing both the ones without the safeguards and with the safeguards. So as you can see here, that the attack succeeded without the safeguards, and the agent would respond wanting to delete the user account. So now we run it with the safeguard. The response is that it's blocked by prediction guard and it could not make a prediction. So it means that the safeguard had successfully blocked the attack, and thus proving that the prediction guard is useful in blocking attacks on in this case, ASI 03.
Now let's talk about what we found, because this is where things get interesting. Without safeguards, the results were honestly alarming. The baseline model showed an 81% vulnerability rate across all OWASP categories. What this means in simple terms is that 8 times out of 10, the model failed. It either followed malicious instructions, exposed data, or performed unintended actions. This is not a small issue. That's a fundamentally unsafe system. But when we turned on prediction guard safeguards, the results shifted dramatically. For what we call input-based attacks, we achieved a 100% block rate. This includes prompt injection, risk 1, PII misuse, risk 2, inter-agent communication attacks, risk 7, trust exploitation, risk 9, and rogue agent behaviors, risk 10. This is a huge result. It shows that for most common and direct attack methods, the ones that try to trick the model through input can be prevented using these safeguards. They don't just reduce risk, they eliminate it entirely in these cases.
But here's where the story gets a bit important. We identify something that we called a logic safeguard gap. So while input filtering worked extremely well, structural risks did not. Specifically, as you can see according to the chart, risk 6 and risk 8, which is memory poisoning and cascading failures. These only saw a 33% mitigation rate. So what exactly is going on here? The key insight that we got from this is that not all risks are about bad inputs. Some risks are just about bad reasoning. An agent might perform an action that is polite, grammatically correct, and completely non-toxic. And it can still be completely wrong and dangerous. For example, deleting a file without permission isn't toxic. It's still a security failure though. So this is where traditional safeguards fall short. They're designed to filter content, not to evaluate intent or logic.
And that leads us to our biggest takeaway, which is that content filtering is necessary but not sufficient. If we want truly safe agentic AI systems, we need to go deeper. We need safeguards that operate at the reasoning and architectural level. So, where do we want to go from here? So, our future work focuses on exactly that. We want to build logic based safeguard layers that can monitor an agent's decision making process in real time, detect unsafe reasoning before the actions are executed, and intervene before failures propagate throughout the system. And then we also plan to expand the test scenarios for deeper OWASP coverage, run more experiments with different models that we switch in and out, and then improve cross model validation to ensure consistency. The goal is to move from simply filtering outputs to actually governing the behavior.
To wrap this up, our project demonstrates that safeguards are not optional. They are not a feature you add later, but they are a foundational infrastructure for any real-world agentic AI system. Prediction Guard was able to effectively close 77% of the total attack surface, which is a significant step forward. But the remaining gap shows us exactly where the future of AI security lies, in understanding and controlling how agents think, not just what they say. Finally, I want to take a moment to thank our mentor, Sharon, and the entire team at Prediction Guard, along with the Datamine, for their support and guidance throughout this project.